Thank you, everyone. I'm actually a doctor and not a professor, unfortunately. Okay, and also apologize, I have a very rough cold. So I'm here on behalf of my group, the Department of Computer Science from University of Pisa. I work with Laura Ricci and Andrea Marino. And this work was about analyzing, so basically graph analysis about the Bitcoin users graph. So which are the keywords? Are Bitcoin, of course, and the users graph. So I assume a basic understanding of Bitcoin from all the participants. And we'll explain very briefly what is the users graph in Bitcoin. So basically, you all know Bitcoin. We have the blockchain, which is a repository of very special data, which is transaction data, so exchanges of value between addresses. And our analyses are especially based on the blockchain up to the end of 2015. This just because we started working on this and the paper published are from this period of time, so not so recent. And also on some external information that we'll explain better later, that is useful to link some known addresses, some very famous addresses to special identities. Like for example, here we have the famous address of WikiLeaks when started accepting Bitcoin donations. So what is the users graph? Basically, there is a well-known attack which is called the anonymization attack against Bitcoin, let's say, anonymity. So the aim of attack is to identify users in the system, so associate each address with a real-world information to identify as a real person or entity. And how this works is that we start from analysis on the blockchain. From this, we build a transaction graph, which basically is a graph where each node is an address, and each edge between two nodes represent a transaction, so fund exchange between the two addresses, present, of course, in the blockchain. Then, through some heuristic rules that we'll see better later, we build a user graph, which is the same graph but clustered, in which each node now is a cluster of previous graph nodes. So basically, each node represents a set of addresses, and this is an approximation of a user. And then, by linking external information to at least one address contained in each cluster, we can identify to a real world link to a real world entity each cluster. So first, a fast recap about anonymity in Bitcoin. Bitcoin does not offer anonymity. It offers a weaker property, which is pseudonymity. So basically, when you want to participate in Bitcoin, you choose an address, which is just basically comes from a random number. It's just public and private key couple. You should create more addresses. So you control a set of addresses, and each address does not carry any information about you. Why? Because of course you generate it from a random number to create the private key and the corresponding public key, and then the base 58 some check encoding. And so pseudonymity means that there is no linking of information between a user and each of his addresses. The second property of pseudonymity is that there is also no linking of information between different addresses belonging to the same user. Again, because they're independent, because they all derive from random numbers. So how can we break pseudonymity? So how can we break those links, those property? Basically to heuristic clustering, which means we adopt some heuristic rules based on behavior of users or rather an intel from user behavior in the network. The most famous example and first proposal was the common input heuristic, which basically means that in a transaction, a transaction is a multi-input, multi-output value exchange, and basically means that all the inputs belong to the same user. This is a very rough approximation, is nowadays often not also true, but was based on the base assumption that to create a transaction you need to sign it, and so the party signing each address needs to be signed, and so the public key needs to be known for each one of the input addresses. Of course, there are ways and a lot of proposals now that use a single transaction, but with a multiple party agreeing to build a single transaction. Anyway, this is in the literature the base the base heuristic used, so the most common and accepted. And this can be done in linear time, linear in the number of addresses and transactions in the system. And so this is the base heuristic we used to obtain the user's graph from the transaction graph during the anonymization attack. So basically we took the blockchain, in linear time we compute this clustering and obtained the user graph. The graph was not so big, so 50 million nodes and 300 million edges. And basically our first step was just to study this graph, so some basic graph analysis. Of course, here we do not have time to show all of them. We show just, let's say, the more interesting, because being Bitcoin a graph about value, about money, we can study the rich get richer phenomenon, which is like more interesting than usual. In fact, in usual graph, richness has many definitions. One can be about connectivity, so the arcs in the graph. But in Bitcoin, since there is actual value, we can also define richness in terms of balance. So studying the weight of the arcs, the edges. And basically, we define the richness simply as the current balance of a user. So basically, just the sum of the inputs minus his payments, so outgoing edges, minus his fees, plus his Coinbase. As we see in the first presentation, Coinbase basically are the miner rewards. So the new block and fees. A lot of properties can be proven. For example, that the richest user at MT are richer than the previous one. So concentration of richness. As we see, the concentration of richness increases in the graph, proving this theory. Another one is that the set of richest users is somehow stable over time. As we see in this graph, the green line is the ever-changing set of richest top users, while in the actual case, the set is a lot more stable. So it means there are some changes, but in the long run, the set is very little, so more or less the same user remains stable over time. And of course, those users are usually exchanges and big addresses. And this is more or less the same from a different catch. So basically here we're studying the top percentiles, normalizing them and seeing that they close. It means that, for example, the top 50% or 75% according to balance percentile gets smaller over time, which means that less people are the richest majority. Of course, we can also use classical measures for inequality. For example, the Gini coefficient. And as we see also for these standardized measures, increasing proves that the richness concentration is valid as well. We did a lot of more analysis, but what was very interesting is that we started with a classical assumption that this graph represented a small world. But this was not true. It was true for most measures, but not for all. For example, if we see the degree distribution, we can see that, yes, it's a nice power law, but we can see some interesting outliers. For example, the one outlier there, which might require further investigation. Moreover, if we see the average distance in the graph, so we studied the distribution of distances, we see that the average distance is very low, so less than 5 for most of the time. Yeah, of course, sorry, on all the graphs, the x horizontal axis is about time. There are number because those are just the time slot we took. We divided the graph, the analysis. Anyway, the average distance remain pretty much constant and very low, as we expect in a small world where there is a very low distance. But the diameter, instead of being logarithmic in the side of a graph and let's say not slowly growing, was very big. In fact, this is the diameter of our last graph, the biggest one, and we can see the diameter is actually 2050. And if we go deeper and investigate how the diameter is built, we see some very interesting patterns. In fact, we can see that the diameter is mostly caused by, let's say, three repeated patterns, which are some mini chains, which basically just pay a little amount out at each step and pay the change to the change address forward. this goes on until the chain is stopped or the value is completely spent. And as we can see in the upper part of the figure, usually new funds are collected and the chain is repeated. So we went further and studied those two anomalies. So high diameter despite low average distance and in degree distribution and also out degree distribution as well, outliers. And what we found was those interesting chains, and those were caused, yeah, that's completely readable, by interesting transactions. Basically what we said, we have the value, we pass the value, and a very little amount which was paid to also famous users. In this case, this transaction depicts user from Bitcoin Talk forum. And what we did was to classify those patterns, both from a transaction and the chain level, and try to give economical meaning to them, so explain why they were built. If we classify those transactions, identify them in the graph, in the user's graph, we can then isolate them and prune them. And if you do this, we see that both the in-degree distribution, which we can see on the right, the old values, so the entire graph, on the left, the pruned values. And we can see that the outlier disappears. And also the diameter, the one of example goes to 9, of course, because we compact all the chains. But also the general diameter gets lower, 5 times lower, which does not seem much. But actually, we expected this diameter as well, and was caused by another kind of chain transaction, not the one classified from this work, but the further one. And so, as we can say, we have discovered some interesting thing that in the Bitcoin graph, the user's graph, we're talking now, we can detect some interesting pattern that cause those anomalies that are not present in regular in other graphs, which basically are caused by the use of using by pseudonymity, so using new address at each time, the use of change addresses, etc., and self-payments. We can detect those patterns, and why is this interesting? Because this can help us to build a better user's graph. In fact, we can define new heuristics. For example, we defined our that's terrible. We defined our chain heuristic based on the example we saw before. So basically, if you have a transaction where we just exchange value at each step, we're paying out a change amount, we can assume that the same user is building this chain. Why? This is, I mean, from a human observation point of view, is kind of intuitive. In fact, we can see that there is a clear structure constant, and so probably the same entity is in charge of the entire structure. Also, if we go deeper and inspect the data, we can see that a lot of those transactions appear together in the same block, which means a high level of trust between the user building the transaction. And because basically you're accepting payment before formal from a Bitcoin point of view, so suggested verification time, so you do not wait for verification. And so doing this, you can define new heuristics. This helps in the heuristic side, so to build the user's graph. We also talked about external information, how we did some analysis mainly to explain the economical meaning, so the semantic of those chains. And how did we obtain those external information? You can use the classical tools, so take from just scraping the web or just a voluntary disclosure. So basically anyone publishes his own address, and so you can link it you can link the cluster to the user. Also, the easiest way is just to interact with the user. So if you want to find out simply an address of an exchange, you just go there, exchange some Bitcoin, and you obtain, of course, his address. And then you can map it back to the cluster with all the other address and obtain the identity of the entire cluster. Also, what we did was we used a network listener we built ourselves. And basically, what does this gives us a very precise kind of information, even if a lot approximative, which is about the IP of some users. Basically, by trying to listen to the first user to relay a transaction, you can somehow map it to some IP with a high degree. I mean, there are a lot of assumptions, etc. but to some extent you can do it, and that's what we have been doing. Thank you.